So let's start by talking about what's happening on a particulate level in a redox reaction. Okay, we know that one substance is oxidized and one substance is reduced, but what does that mean? Just like most things in chemistry, it comes down to electrons. So we can see in our oxidation states and in our reactions that if a substance is oxidized, its oxidation state goes up. It becomes more positive. We also know from our first year chemistry class that when something becomes more positive, it loses electrons, right? It does require a little bit of a shift of thinking because we normally think as positive as a gain, but in chemistry, because electrons are negative, positive means it lost electrons. So when something is reduced, the oxidation state goes down, which means it gains electrons. So an acronym that people use is oil rig. Oxidation is loss, reduction is gain. So if you remember oil rig, that will help. You also might see this acronym, LEOGR. Loss of electrons is oxidation, gain of electrons is reduction. I think oil rig is more common, but LEOGR is there too. So if you see that, it's the same basic idea. Use whatever one makes sense to you. Down here is just a little background on these terms. They basically come from when these types of reactions were first studied. So you can look through that. It really not something you need to know, just a little bit of background information. So let's talk about some terms, okay? This graphic is a reaction. It's just a generic reaction that looks something like this. In this graphic, the top part is the A plus B part, and the bottom part is after the reaction happens when they are combined. So what we talked about last video is that A is oxidized because the oxidation number goes up. We just learned that means it loses electrons. B is reduced because the oxidation number goes down, and we just learned that's because it gains electrons. So both of these things have to happen in order for the other one to happen. So A can only lose electrons if it has somewhere to put them. B can only gain electrons if it gets them from somewhere. Okay, so we really didn't talk about the relationship between that in our last video. We just talked about the numbers. So now we're saying, okay, so what's actually happening in a redox reaction is that one substance is giving electrons to another substance. The substance that is oxidized is giving those electrons to the substance that is reduced. So we're also throwing out two new terms, reducing agent and oxidizing agent. Whatever substance is oxidized is also known as the reducing agent, because agent just means it kind of facilitates something. So if it's the reducing agent, it is allowing B to be reduced. B, on the other hand, is the oxidizing agent because it's allowing A to be oxidized. Like we said just a minute ago, A can't be oxidized unless it has somewhere to put those electrons. So B is known as the oxidizing agent. And there's always this correlation, okay? It's always that whatever's oxidized is also the reducing agent, whatever's reduced is also the oxidizing agent. So let's jump into the first real topic of this video, which is half reactions. When a redox reaction occurs in aqueous solution, so not combustion, combustion is redox, but it's not in solution, and then some other ones wouldn't apply here either, we can separate it into half reactions. One half shows oxidation, and the other half will show reduction. Okay, so let's talk about how to do that. So the first thing I'm going to do is write the net ionic equation. So here it would be Zn plus Cu2 plus, so 4, 2 minus, Cn2 plus, SO4 2 minus, Cu. We can then cross out our SO4 2 minuses, so we end up with Zn plus Cu 2 plus gives us Zn 2 plus Cu. So next step, separate them into half reactions. So what you'll do is you take the substance that is oxidized, and that's going to be 1/2, and then the substance that is reduced is the other half. So here we'll have Zn gives us Zn2 plus, Cu2 plus gives us Cu. Now you'll notice I wrote them kind of weird. We're going to be adding reactions a lot, or half reactions a lot this year, and it's much easier if you line up the arrows. Okay, so I would like you to get in the habit of doing that. So step number 3 says to add electrons. I'm just going to do it right up here rather than writing the whole thing again. So one thing that we talked about in the net ionic portion of this course was that the charge needs to be balanced on each side of the reaction. So if you look, it's not here. We have no charge before the arrow and a 2 plus charge after it. So what you can do to balance them is add electrons. So if we add 2 electrons here, now we have no charge after the arrow as well. And if we do the same thing here, the charge is balanced on both sides of the reaction there as well. Now the last thing here says to balance. I would just check. It's important to check for 2 things. I'm going to get into that. But if you balance it along the way, like make sure your net ionic is balanced, etc., you should be okay here. So just check to make sure it's balanced. And when you do that, you don't want to just check atoms. You don't want to just check atoms in charge. You also want to make sure you have the same amount of electrons in both of the half reactions. Now, you don't need to have the same amount of atoms or anything like that, but you want to have the same amount of electrons. And we'll talk more about why later on in this video. So here we have 2 here, 2 here, we're good. So this is our final half reactions. So let's do a couple more examples. Oops. So I'm going to write my net ionic equation here. But this one, if you notice, it's not balanced. Okay, the other one was already balanced. So what I'm going to do, and you can refer back to the net ionic to see what your options are here, but I'm going to go ahead and balance it now. That makes it a little bit easier on me. So I'm going to have Cu plus 2Ag plus, plus 2NO3 minus gives us Cu2 plus 2NO3 minus plus 2Ag. So in this case, the 2NO3 minuses will cancel. And then I'm going to split them up into half reactions. So Cu and Ag. And then I need to add electrons to balance this out. So I'm going to put 2 electrons here and also 2 here. Now it might look like I only need 1 here because this positive sign, but don't forget the coefficient. This 2 here means we have 2 Ag positives. Okay, so if we have 2 Ag positives, 2 positive, we need 2 electrons to cancel that out. So this will be our final half reactions. So let's try one more. So here for your net ionic equation, let me balance that first. You're just going to split this up. Okay, so because the first 2 are just elemental forms, they're not going to break apart in solution. But then your KBr will. So we're going to split it up and end up with 2K gives 2K plus, and Br2 gives 2Br minus. Now this is a little different than the other 2 examples we did because we have some minuses in here, okay? But the process is the same. We're going to make sure the charges are the same on both sides. So our first one, we have no charge before the arrow and 2 plus after the arrow. So we're going to add 2 electrons to make them both have no charge. And for our second one, we have no charge before the arrow and 2 minus after the arrow. Okay, so what I'm going to do is make them both 2 minus. Both sides of that arrow are 2 minus. Now you don't have to have the same charge in each half reaction. As long as each half reaction is balanced and you have the same amount of electrons, you're good to go. Okay, so here we don't have to make this second one have no charge just because the first one does. It's fine if we have a 2 minus here and a 2 minus here. So this is our final 2 half reactions. All right, so here's some practice. So if you want, you can go ahead, well, you should go ahead and pause the video and do this on your own, and then come back here to see the answers. So I'm not going to write out the net ionic equation here. I'm just going to write the answers. So that's for number 1, our 2 half reactions. Number 2, I'm going to do over here so it's easier to read. So that's number 2. And that's number 3, those half reactions. Okay, so I labeled these next few as practice because I'm not going to go over the content is still the same, okay? So I labeled these next two as practice. So you can go ahead and try them. If you don't feel confident, then you can watch me do them, okay? So I will go over them more in detail. So here we're going to add these together, all right? And I'm going to rewrite them so that the arrows are lined up, because I think that's very helpful. Whoops. Don't know how that got up there. All right. Now you might notice right away that the second one isn't even balanced. So I'm going to put a 2 there to balance it first. And then I'm going to add them together. Okay? So when you add them together, you can do it one of 2 ways. You can cross stuff out in the half reaction stage, or you can wait until you put it all together and anything that shows up on both sides you cross out. So I'm going to do the second way, excuse me. So I'm going to do Cl2 plus 2E minus plus 2Br minus. Okay, so all I did was take everything before the arrow and add it together. And then everything after the arrow is going to be put together. 2Cl minus plus Br2 plus 2 electrons. Now, because I have 2 electrons on both sides, just like in your net ionic equations, you can cancel those out. And that's kind of what I was hinting at before. We don't want an overall reaction, either net ionic or full, to have electrons in it. Half reactions, totally fine. But when you're adding them together, you want to make sure that the electrons will end up canceling. And so that's what I was saying, that when you write your half reactions, just do an extra check at the end. So this will be our final reaction. All right. So here's a quick and easy one. Hopefully you can pause this one and do it on your own, because it's really just asking how many electrons need to be added here. Okay, and to make this work, we would need 3 electrons on the product side, because we have no charge here, 3 plus charge here. So when we add 3 electrons, we end up with no charge on both sides. So here's the same idea. It just has a little bit more to it. Okay, so this has some more charges going on. We have 8 positives here, because we have a coefficient and that positive charge. Plus we have 1 negative. So overall, we have positive 7 before the arrow. Okay, so because if you add 8 positive plus 1 negative, you get positive 7. Overall here, we have 2 plus. So the question is asking how many electrons should you put to make sure it is balanced? You're only going to put them in one place, okay? Because like we said before, they would cancel out if they're on both sides. So what I'm going to do is get both sides to be 2 positive. So if I took this and added 5 electrons, I now have an overall charge of 2 plus on both sides of the equation. So the answer would be 5 electrons. And if I asked you on what side, you would say on the left or on the reactant side, which the practice questions will, some of them will ask that. All right, so that's it for half reactions, the first topic in this video. Now I want to move on to something called redox titration. Now we're going to talk about titration at length forever in the acid-base one, and it is way more complicated with acid-base than it is with redox. Redox titration is essentially a stoichiometry problem. Okay, so and a lot of AP Chem will go back to stoichiometry. So titration itself is when we use one substance to figure out how much we have of another substance. Okay, we will do a lot of these in class. We're going to have those big burettes you probably didn't use in intro chem, and we'll use them here. I really like titration. I think it's a really fun process, so we're probably going to do quite a few of them. But basically, the general idea is that you're using one substance to figure out how much you have of another substance. So in redox titration, the reducing substance is titrated with a solution of a strong oxidizing agent, or the other way around. The oxidizing substance can be titrated with a strong reducing agent, okay? The most common oxidizing agents are listed here. You're going to see them a lot in the AP practice problems, KMNO4, K2, CR207, and so on, okay? You'll see those a lot. KMNO4 in particular is a really cool one. So here is the reaction for it. The reason it's really good is because in titration, a lot of times you'll add what we call an indicator. And you may have heard of indicators with acid-base in intro chem. An indicator will change color when something happens, and they all have different things that they indicate. So what's nice about potassium permanganate is that it's its own indicator, okay? So when you have potassium permanganate in solution, it's going to be MnO4-, which has a purple color. And then when all of that is used up, we're going to have Mn2+, which is colorless. So that's what's nice about this, the KMNO4, because you can see the change without an indicator, okay? So this is just a little bit of background. The actual mechanics of titration will be a lot more clear when we do them, when we start doing titrations. So we'll get there. That won't be an issue. We'll probably do a redox titration relatively soon. And then, but for right now, we're just going to talk about the actual problems. Okay, so let's take a look. I'm going to do 2 examples and then give you 2 practice. Like I said, they're mostly stoichiometry. So here we have 0.264 grams of sodium oxalate is dissolved in a flask. That means it's dissolved in water in a flask. And requires this much potassium permanganate to titrate it. Here is the overall crazy pants equation for this reaction. Okay, we will need that because we will be using coefficients for stoichiometry. The question is, what is the molarity of the potassium permanganate? Okay, so to do this titration, or to do any titration, you're going to want moles of your 2 substances. Okay, because moles are going to be what compares different substances. You can't compare grams, you can't compare milliliters, but you can compare moles. So the first thing I'm going to do is figure out the moles of KMNO4. Okay, now you could first figure out the moles of sodium oxalate and then do the moles of KMNO4 and 2 different stoich problems. That would be fine, but it's much easier to do it in one, I think, and we know how to do that. So to find the moles of KMNO4, I'm going to take my given moles of sodium oxalate, because we know that that entire thing reacts, okay? That's what we mean by the end point, okay? So that entire thing reacts. It goes from sodium oxalate, and then it's going to be in that Mn2+ that we have here. Well, I mean, we're doing this one backwards, right? Yeah, because we're adding the KMNO4. So we're going to wait till it turns that pink-purple color. Okay, so we know that the entire sodium oxalate reacts. So we're going to take that grams of sodium oxalate, and we're going to convert that to moles of KMNO4. So first we have grams to moles of sodium oxalate. And then we're going to go from moles of sodium oxalate to moles of potassium permanganate. And this is where we need the reaction, okay, because we're going to use the coefficients as our mole ratio. So that gives us moles of KMNO4. Now, what they're asking for here is the molarity of KMNO4. So molarity is just moles over liters. So we have the moles here. The liters are in the problem, okay? It says it took 30.74 milliliters. So we're just going to convert that to liters and plug it into our molarity problem, our molarity formula. And then that comes out to 6.4. Okay, so that was the molarity of KMNO4 that we used in the titration. So let me just go back, because a lot of what we're going to be doing in this class is talking about what's actually happening, okay? Because it's not as easy as intro chem, and I've said this before, that you can just follow the rules and get the answer. So let's talk about why that worked, why that situation worked, okay? So what we needed to figure out was how many moles were in our 30.74 milliliters. Okay, that's what we needed to figure out so that we could plug that into the molarity formula. So we knew the moles, we knew the liters, we needed the moles so we could get molarity. In a titration, you are adding the exact right amount of the thing you're using. The titrant is what we call it. You're using the exact right amount of it, okay? And when we do these in the lab, you'll see we add drop by drop from the burette so that we get the exact right amount. So what that means is that we used our 30.74 milliliters was the exact right amount of KMNO4 to react with the 0.264 grams of sodium oxalate. Okay, we had no limiting reagent in this problem. They were the exact right amount. Well, I should say we had no excess reagent. We had no excess of either reagent. That's what titration is all about. It's about getting the exact right amount. So if we know that we titrated correctly, and we're going to assume we did in this problem, in any problem, if we know that we titrated correctly, we have the exact right amount of KMNO4 to react with this exact amount of sodium oxalate. So that is why I was able to use this stoichiometry problem. Okay, so we're saying that I reacted this entire amount, the 0.2640, so I can use that to figure out the moles of KMNO4. Okay, because we know that that's what the mole ratio is all about. We can use that information. So that's how I was able to use that to get the moles that were in that 30.74 milliliters, because we knew that we had the exact right amount. And that's what titration is all about again. So all that we're doing here is a stoichiometry problem. We're just adding some lab stuff into it. So let's try another example. So potassium dichromate, that's another one of the things we said, it's very common, is used to titrate a sample containing an unknown percentage of iron. The sample is dissolved in acid to reduce all of the iron to Fe2+. The solution is then titrated with, we're given the molarity here, producing Fe3+. So this is our oxidizing agent, the potassium dichromate. And so you can see that we're oxidizing Fe2 to Fe3. And then you'll also see that it talks about acidic solution. So that's something that AP has taken off the exam. A lot of times redox occurs in either acidic or basic solution. You don't have to know about that, but you will see it in the problems, okay? That is not something that AP is requiring you to know about anymore. So just kind of ignore that if it's there. Okay, the titration requires 32.26 milliliters of our potassium permanganate. And then we have this of the sample. And then we have a reaction here. This is really funny because I guess that when I copied this one, I did not put the actual question. So the question was, what percentage of iron was in that sample? Okay, so what is the percentage of iron? Okay. So let's think about what we would need, if we work backwards, what we would need to figure out what percentage of the sample was iron. We're going to need to know the grams of iron. Okay? So what we need is grams of iron. Once we have that, we can just do a simple division to figure out the percentage because we have the grams of the total sample. Okay, so this one's kind of working backwards from the other one that we used. We're still going to do stoichiometry and we're still going to use our molarity formula, but it's going to be a little different because this time we're given the molarity. All right, so what I would need is the moles of potassium dichromate, because I can then use that moles to get to the moles and grams of iron. So first I'm going to figure out the moles of potassium permanganate. So the moles, potassium dichromate. So that's going to be the molarity times the liters, right? Because we know our molarity formula is moles over liters. So if we want moles, we do molarity times liters. Okay, so if I do molarity times liters, I have And then our liters. So we have this many moles of potassium dichromate. So what I can now do is a stoichiometry problem going from moles of potassium dichromate to moles of iron, and then grams of iron. So I'm going to do that all in one thing. Moles of potassium dichromate to grams of iron. So I'm going to start with moles of potassium dichromate. So if you look at this reaction that they gave us, it's a net ionic reaction. Okay? There is no potassium dichromate in this reaction because the potassiums would cancel. So I'm going to add a little extra step here. Okay? And it's not going to end up mattering for this problem, but in the future it might, and I want you to be thinking about this. It was also on the summer assignment. So when we go up to this reaction and try to find the mole ratio, we can't find the mole ratio of potassium dichromate because it's not there. So what I'm going to do is go to moles of dichromate. And all that, and then for this one, like I said, it doesn't matter because it's a 1-to-1 ratio. Okay, so all that means is that in potassium dichromate, when it dissociates, how many moles of dichromate do I get? And it's just 1. Okay, so if it was something like, let me just erase that. If it was something like when MgCl2 dissociates, how many moles of chlorine do I get? You would get 1 mole and then 2 moles of chloride. Okay, so in that case, you would have to have a different 1-to-1 ratio. But here, because when you dissociate potassium dichromate, you get 1 mole of dichromate. So I'm going to put that in there because that is something you should be thinking about, but don't worry about it for this problem. So now we can use the mole ratio and go to moles of Fe2+. So for every 1 dichromate, we have 6 Fe2 ions. And then we're going to figure out what grams that would be. So you can put Fe or Fe2+ there. Remember that electrons don't factor into the mass. Okay, so electrons' mass is negligible. So when we look up the atomic mass of iron on the periodic table, we can assume that's also for iron's ions. That's confusing to say. Fe's ions. We can assume that the mass is the same because the only thing that changes between Fe2+ and just regular old Fe is that Fe lost 2 electrons, okay? And that doesn't affect the mass. So we can use that mass for the ions as well. So that gives us .1758 grams of Fe. And then we need to figure, so that just gives us the grams, but the question was, what's the percentage? So to figure that out, you just divide this by the total grams of the sample. and multiply by 100. So that comes out to 13.77% iron. So that one seems a little more complicated than the first one. And quite frankly, if you need to go back and watch those two being done out again, I think that's a great idea. Keep in mind they both follow the same basic pattern where we're using the molarity formula and a stoichiometry expression to solve one of these problems. Okay? So again, if you need to go back and look at that, please feel free to do so. And then come back and try the practice. So here is the first practice problem. So I would suggest pausing it here, trying this practice on your own, giving it a shot, and then coming back to see the answer. So this one is a lot like the one we just did. And now we're finding the mass and the percentage. So we're going to start by finding out the moles of I3 minus. Okay, so just so you know, 3 is the subscript, minus 1 is the charge. In case that wasn't clear. I tried to make it really clear, but in case it wasn't clear. So what you're going to do first is find the moles of I3 minus. And to do that, you're going to multiply the molarity times the liters. And then we're going to use that to get grams of tin. I'm sorry, I paused because I kind of skipped over a part here, but again, it doesn't matter. Okay, so this is moles of I3 minus. It's actually going to be, let's change that to keep it consistent with the one we just did. Moles of NaI3. I just want to keep it consistent with the one we just did. Good. All right, so now we're going to take that moles of NaI3 and move that to and change that into grams of tin. So we're going to start with moles. And then we need to do that extra step to figure out for every 1 mole of NaI3, how many moles of I3 do I have? Now this one is very confusing because it seems like it should be NaI, but remember it's a polyatomic ion, not one that you need to have memorized, not one that's very common at all. But it's a polyatomic ion, I3, okay? So for this one, you would have 1 mole of I3 minus, okay? And it's, again, not one you need to recognize, but you should be able to recognize that it is a polyatomic ion because it has a subscript and a charge. That's what I was getting at, explaining that before, okay? So you should be able to say, oh, that's a polyatomic ion, even though I don't have that one memorized. So when NaI3 dissociates, it dissociates into Na plus and I3 minus. Oops. All right, so then we'll do mole of I3 minus, 2 moles of SN2 plus. They both have a 1 in front of them in the reaction. So then we'll do 1 mole and so that comes out to 2.284 grams of tin. That's the first part of what they're asking for. And then we also need the mass percentage. So we take that. What is it, 10 grams? 10 grams for the sample. Times 100. So that's the second part of the answer. All right, so here's one more practice. You can pause it and try it on your own. Okay, so we have our liters and our molarity of Ce4 plus to oxidize the Fe2 plus. Molarity. Okay, so we're going to find the moles of Fe2 plus and then also the grams and convert that to milligrams. So this one is a little different in the terms of the molarity because they're actually telling us the molarity of the ion. The other two examples we did, they told us the molarity of a compound. So we had to do that extra step where we figured out how many moles of the ion would be in the compound, whatever. Here we don't have to do that, okay? So what we're going to do first is find the moles of Ce4 plus. And that we're going to do the same way, molarity times liters. And that gives us okay, so that gives us our moles here. Okay, so for this one, for this problem, we need the molarity and the mass. So what I'm going to do is just a quick 2-factor stoichiometry problem to find the moles of Fe. And then I can easily convert that to grams of Fe. But since I need the molarity of Fe2 plus, I'm going to need the moles. So to do that, I'm just going to do moles of Ce4 plus, 2 moles of Fe2 plus. So here, they're both 1s, so it's going to be the same. And if you recognized that, I mean, even if this was a free response question, if you recognize that they had a 1-to-1 mole ratio and they're going to be the same, if you wanted to just say that instead of doing out the math, that would be fine. It doesn't matter if you explain things in math or words. Okay, so now we have our moles of Fe2 plus. So to find the molarity, we're going to do the moles over the liters. And we had 35 milliliters of Fe2 plus. So here is the first part, a molarity of Fe2 plus. So now I'm going to figure out the mass of iron in the sample, okay? Now this is not hard. This is just a regular stoichiometry problem. Where people might get confused is if they're not being careful here and they try to use the molarity to go to moles. To go to grams, excuse me. You're not going to do that. That's not what you use in stoichiometry. You use the moles. Okay, so even though we already found this, we don't need it. We're going to go back up to this number right here and use that to find grams. So we take the moles and use that number. So that comes out to this, but they ask for milligrams, so we'll convert that to milligrams of iron. And again, it's easy. You can, when you're talking about mass, you can just switch from Fe2 plus to Fe because the electrons don't matter for mass. Okay, so that is redox titration. Hopefully you kind of grasped it a little bit, and don't forget that we'll be doing these in class, so you can definitely ask questions as we go through, or watch the video again, whatever you need to do to make sure you have a little bit of a grasp on it when you come into class next.